In the last few videos, I've talked about how to model qualitative predictors using indicator variables. And I'm going to move on now to talk about some possible pitfalls when you're doing multiple linear regression modeling. And in this video and the next two videos, I'm going to focus on influential points, so looking at individual points and how much influence they could potentially have on the model results. And then after that, we'll go on and talk about some other pitfalls. So what are influential points in the context of multiple linear regression modeling? So what I'm talking about here is that we need to be careful about making conclusions from our model results if those are being overly influenced by just one or two or a small handful of data points. So for example, the overall results can be quite biased if there's a few unusual points in the dataset that differ dramatically from the general patterns in the majority of the data. And so it's clearly going to be misleading if we're concluding evidence of, say, a strong association between variables if that evidence is based solely on a few dominant points. So we're going to focus on two measures of individual data point influence, and these are quite distinct, so it's important to keep these ideas separate, and so we're going to focus on them separately. So first we're going to think about what in multiple linear regression are called outliers, and these are data points that have unusual response values relative to their predicted values from the model. So in other words, there's a very big difference between y for that data point and y hat, which is the predicted value from the model. By contrast, another type of influential point are what are known as high leverage points. And so these are points that have very unusual combinations of predictor values relative to the patterns that we're seeing in the rest of the data set. So the distinction here is outliers are talking about points that have unusual response values, so unusual values of y, whereas high leverage points are points that have unusual x values, so unusual predictor values. And then we're also going to look at a measure that is, if you like, a composite measure of both of these concepts. So it considers points from the perspective of both, whether they're likely to be outliers or high leverage points. So in this video, I'm going to focus more on outliers. In the next video, I'll talk about leverage, and in the third video in this little sequence, I'll talk about Cook's distance. So let's talk about outliers. So as I just introduced, outliers are data points that have unusual response values relative to their predicted y hat values from the model. So if you remember back to when we talked about checking assumptions in a regression model, we defined residuals as the difference between y and y hat. So in other words, outliers are going to be data points that have very large residuals. So if we're thinking about, well, what does that mean, a very large residual? Well, the residuals are measured in the same units as the response variable, and so it's difficult to say, well, how large does a residual have to be before we have to start worrying about it being an outlier? And so we need to standardize those residuals somehow, so across different applications we have a common measurement scale. And so there's various ways that residuals can be standardized, but the way that I'm going to focus on here is something called studentizing the residuals. And essentially what studentizing does is it puts the residuals on a common scale so that when we think about the four regression assumptions that we talked about earlier, so zero mean, constant variance, normality, and independence, then the studentized residuals have an approximate normal distribution with a mean of 0 and a standard deviation of 1 if those 4 assumptions are satisfied. And so given that, so thinking about our understanding of the normal distribution, we know that the majority of a standard normal, so we're talking about a standard normal distribution here, so the majority of observations for a standard normal distribution are going to be within plus or minus 3, and so that gives us a useful rule of thumb for designating an outlier. So we're going to say a data point is an outlier if it's got a studentized residual that's outside of this range. So it's either bigger than plus 3 or smaller than minus 3. And so the rationale for this comes from the thinking about the normal distribution. If we were to see a data point with a studentized residual outside plus or minus 3, then we've either witnessed something that's extremely unusual, and so thinking about probabilities associated with a normal distribution, what we're talking about here is something that's got a probability of less than 0.002, so very small probability, or we found an observation that has a y value that doesn't fit the pattern in the rest of the data set, and so we need to think about what we're going to do in that circumstance. So if we run an analysis and we find an outlier, so in other words a data observation that's got a studentized residual bigger than plus 3 or smaller than minus 3, then we need to think about what we're going to do about that observation. So there's a few possible scenarios here. It's possible that this is simply a data entry error. And so if we go back and look at the data set that we're analyzing, we might discover that someone's mistyped a number. And so that's very easy to deal with. Just correct the mistake and off you go again. Another possible scenario here is that there's actually nothing wrong with the data. It's our model that's deficient. And so, for example, we might have neglected to include an important predictor. And so if we go back, reanalyze the data with that predictor included, we end up with a better model, and all of a sudden that data point that we identified as an outlier in the first model is no longer an outlier in the second model. The new model with the important predictor is able to get a better sense of the patterns in the data and gives us a predicted value y hat for that observation that no longer differs greatly from its observed response value, and so it's no longer designated an outlier. Another possible scenario is that when we were to do a residual analysis and look at checking the assumptions, so checking the zero mean assumption, the constant variance assumption, and so on, it could well be that this model doesn't really satisfy those assumptions very well. And so that's another signal that the model is deficient, and so we need to kind of go back to the drawing board and improve the model somehow to come up with a model that does satisfy the assumptions. And so the outlier that we discovered is a signal that something is amiss, and in this case it's because the model doesn't satisfy the regression assumptions. And then a fourth possible scenario here is that this outlier, it really is very different from the other data, and there's nothing wrong with the data, there's nothing wrong with the model, everything's good, it's just we've got a very unusual point. And so in that case, what we might think of doing here is to say, okay, well, this data point doesn't really fit here, and so I'm going to exclude it from the analysis. I'm going to come up with a good model that works for all the other data, and I'm going to report that when I did my analysis, I found this kind of rogue point that was an outlier, doesn't really fit with the rest, and I don't really know why, but I'm going to flag it, and in the meantime, here's a model that works for all the other points. So how are we going to deal with the question of determining how much of an influence an outlier that we've discovered is having on our model? Because let's say we've found an outlier, it's possible that although that point is different from all the others, it doesn't actually have much of an impact on the model, in the sense that if we were to exclude that point and reanalyze the model for all the other points, that we end up with a very similar model in terms of the coefficient estimates, how well the model fits, and so on. And so that's the strategy that we're going to use here, is if we analyze a data set and find an outlier, we're going to remove it from the data set, reanalyze the model to all the other data, and see whether things change much. And if they do, then our conclusion is going to be, yes, this outlier is having a big influence on the model, and so I need to flag this. On the other hand, if taking that outlier out of the model doesn't really change much, we're just going to maybe leave it in the analysis, because whether we include it or exclude it doesn't have much of a difference, and so we're just going to leave it in the model, because we're just going to assume in that case that we're just seeing something unusual, which can happen. Unusual events doesn't mean impossible, it just means they don't happen very often. So let's look at some actual data. So I'm going to go to R here, and this is some data on some cars where we've measured the fuel efficiency in miles per gallon in the city, engine size, number of cylinders, and the interior volume of the car. So this is a measure of kind of how big the car is. So the way that we're going to analyze this data is we're actually going to transform the response variable here so that we're looking at gallons per 100 miles instead of miles per gallon. And the reason is because from an engineering perspective, it makes more sense to analyze the data this way. So we'll fit a model with the three predictors: engine size, number of cylinders, and volume. And if we just take a look at the coefficient estimates, we can see 2.542 for the intercept, 0.235 for the regression parameter that goes with engine, and so on. And so at this point we might go, okay, well, everything's great. I'm gonna use these coefficient estimates. That's gonna help me predict the fuel efficiency of a car if I know its engine size, number of cylinders, and volume. And off I go. But hold on. If we take a look at residuals from the model, we see something a little bit alarming. So this is a plot of residuals on the vertical axis and fitted values from the model on the horizontal axis. And we can see that most of the residuals are kind of up in this range up here, but we've got this point here that R has flagged as car number 32, which has a negative residual that's much further away from all these other points than we would like. It's really extreme. So let's look a little more closely at this. Let's calculate the studentized residuals. Actually, let's just get rid of that, and okay, let's look at the studentized residuals. And I could draw the studentized, I could plot them in a histogram. Let's do that. So we can see, okay, here's all my studentized residuals. Most of them are between plus minus 2, except this one, it's really extreme. Our designation for an outlier was anything outside plus minus 3. This is less than minus 8. Okay, it's very definitely an outlier. So this point, it's got a studentized residual of minus 8.3. We'll just confirm that it is car number 32. What is car number 32? It looks like it's a Lexus HS250H. Okay, so this particular car is an outlier in this model. Okay, so what's going on here? Well, if we were to look at the details for this car, we would discover that this car is actually it's a hybrid. Okay, all the other cars in the data set are regular gas-powered cars. This one's a hybrid, so it's got a relatively high miles per gallon based on its engine size and number of cylinders and interior volume. So this car is not fitting the pattern of the rest of the data. So in this case, I think it's fair enough to exclude this car from the analysis because it's not the same as all the others. Okay, it doesn't really belong in this analysis. If we're trying to build a model for fuel efficiency of gas-powered cars, it's kind of silly to put a hybrid in there. Okay, so let's do that. So what I'm going to do is I'm going to create a new data set that excludes that Lexus, and then I'll redo my analysis. Okay, so what happened with my regression parameter estimates when I did that? So let's look at, for example, the regression parameter that goes with engine. It's 0.26 in this model, and in the other model it was only 0.235. Okay, in the first model that had the outlier, the regression parameter with cylinders is 0.294, and now it's 0.228 with this model. And with this model, the regression parameter with volume is 0.492, and before it was 0.476. Okay, so we're getting very different regression parameter estimates now that we've excluded that outlier. Let's calculate the studentized residuals again, and let's look at the residuals versus fitted values again. So this is for the model that excludes that Lexus, and now we don't have a point that's got like a weird really extreme residual. And we can see this also if I draw a histogram of the residuals. Okay, now they're spread between +2 and looks like -2.5. Okay, so we don't have any more outliers in this data set. So this illustrates one possible scenario. We fit a model to some data, and when we looked at a residual plot, we observed that we had a residual that was much more negative than all the other residuals. And when we calculated the studentized values, the studentized residuals, we discovered that that studentized residual was actually -8 point something, -8.3 I think, well outside ±3, so we designated it as an outlier. And then we did a little bit of digging into the details for that particular observation, discovered that it didn't really belong in this analysis. We were trying to model gas-powered cars, and it was a hybrid, and so it doesn't really belong, so we excluded it. And then when we reran the analysis, we obtained regression parameter estimates that were very different to what they were before. So it was critical that we excluded this car that didn't belong, because before we were getting a very misleading regression equation, and now we've got a regression equation that's much more appropriate for the data. So that's an introduction to outliers. So remember, outliers are observations that have very unusual response values. Next, we'll look at observations that have very unusual X values, so very unusual predictors. And we'll look at that type of observation and how much of an influence that kind of observation might have on a regression analysis.